Okay, today's lecture is going to be on sustainability, and I'm James. And if you've got any questions at the end of the lecture, just feel free to drop me an email, or I can arrange some Zoom times when we can have a chat. So today's content, we're going to be starting off by taking a look at sustainable development. Then we're going to discuss the Earth's timescale shift from the Holocene to the Anthropocene epoch, life cycle assessment for the built environment on a global scale. After this, we'll take a closer look at New Zealand, following on to discuss the proposed action for tackling climate change in New Zealand, with some recent updates that we have received since January the 31st. Number 6, accreditation issues for sustainable development. Then we'll look at the Structural Engineering Society of New Zealand, CSOC, with the comparable profession body there being the Institution of Structural Engineers in the UK. And finally, we'll finish off by looking at different sustainable developments around the world. So what is sustainable development? Sustainable development is a development that meets the needs of the present without compromising the ability of future generations to meet their own needs. And that's from the Brundtland Report 1987. And if we consider the 4 capitals, first one is natural resources, accounting for the available land, soil, water, plants, and all other natural resources available to us. Number 2, human resources, accounting for the capabilities of people to engage in work, study, recreation, and social activities, includes skills, knowledge, physical, and mental capabilities. Number 3 would be the social resources, accounting for the norms, rules, and institutions that influence the way in which people live and work together and experience a sense of belonging. And finally, the last one is the financial and physical resources, accounting for the financial and human-made produced physical assets, usually closely associated with supporting material living conditions. This includes factories, equipment, houses, roads, buildings, hospitals, and financial securities. Now, why do we need more sustainable development? We have moved on to the next stage of the Earth's timescale from the Holocene, where we had stable climatic conditions for 12,000 years, to the Anthropocene epoch. This means anthro for man and C for new. The Anthropocene epoch has been caused by human activities that have led to mass extinctions of plant and animal species, polluted the oceans, and altered the atmosphere, amongst other lasting impacts. Human activities have caused climate change, ocean acidification, chemical pollution, nitrogen and phosphorus loading, freshwater withdrawals, land conversion, biodiversity loss, air pollution, ozone layer depletion. We are in unknown waters with our own natural world, and it could be on the brink of mass extinction, as we can see on the picture on the right. As individuals and engineers, there must be something that we can do. Sir David Attenborough on the Earth's current state. There's a video you can watch, Continuation of Civilization is in Your Hands. From this video, we will see that David Attenborough discusses the collapse of civilization and extinction in the natural world. He also outlines how the United Nations brings us together as a planet to tackle the Anthropocene epoch. David puts responsibilities of continuing civilization into our heads, or into our hands, which I think I think that as some civil engineers we should all agree with that. So, taking a look at our main contributions of greenhouse gases around the world, where do you think New Zealand is ranked? New Zealand is ranked 5th in the world for greenhouse gas emissions, with agriculture and the built environment being the leading contributors for this in New Zealand. There's a video on the greenhouse effect. The video outlines the process of which greenhouse gases are generated, causing our Earth's timescale to have to shift to the Anthropocene epoch. If you watch the video, you will see that human activity has caused a global emergency to tackle the greenhouse gases that we emit on a daily basis. They also talk about the measure of greenhouse gases being measured as an equivalent to CO2. 28 tons of CO2 equals 1 ton of methane, which should be used in agriculture. 298 tons of CO2 equals 1 ton of nitrate oxide used for fertilizers. 22,800 tons of CO2 equals 1 ton of fluorinated gases, which are extinguishing agents. Finally, it's discussed the various ways that we can tackle greenhouse gas emission, of which we see later on in this lecture. Early contributors to the greenhouse gas effect in the built environment, considering construction material manufacturing process and the construction process for New Zealand developments only, meaning exported construction materials are not included. This accounts for 6.2% of New Zealand's carbon footprint. From this 6.2%, aluminium and steel production account for 61.3%, and cement production and other non-metallic minerals account for 30.6%. From this, sometimes we can think about whether a change of material is what we need. Carrying on from the previous question, material science for a standard projects that require structural framing, the use of structural steel and concrete could be replaced with sustainable structural timber or glulam. Development life cycle. Developing a structure that requires a very high level of maintenance throughout its life cycle. A key example here would be the Golden Gate Bridge in San Francisco that requires painting every 7 years to protect it from the saltwater corrosion. Number 3, non-energy efficient developments. Developments that require very high levels of energy to operate throughout its life cycle and does not generate its own energy. Material required to manufacture the electrical transmission, towers and cables is known as sulfur hexafluoride, SF6. This is the most powerful greenhouse gas. We need to be aiming for energy and water net usage to be zero. Further contributors. Construction methods that we adopt are another major issue, with the global built environment accounting for 39% of carbon dioxide emissions. It holds an extensive proportion of carbon dioxide released on an annual basis. Taking in situ construction as the original construction method, some typical pollution types during this process are noise, dust, environmental, social, and so on. The question we must ask ourselves and our nation is, how can we transform our construction methods to cause less pollution with the resources we have available to us? In this, we must consider the natural, human, and social, financial, physical resources. Non-collaborative working is another major issue that is causing additional greenhouse gas emissions. This is mainly caused by people not working together, which leads to mistakes. An example is not using an up-to-date drawing on site. How can this be tackled? Perhaps through building information modelling? These are just some of the examples that have caused global built environment to be a main contributor of greenhouse gases around the world. In this lecture, we're going to be breaking down the various, how can we embed sustainability as a journey for the built environment? By moving forward using life cycle assessment for all new and existing developments. So we're going to be breaking down the various stages of life cycle assessment to analyze what we are doing and how we can do it better. First of all, look at the raw material extraction. The next stage involves how we are going to process that raw material. After processing the raw material, we need to think about how we are going to manufacture the building parts from the processed material. From these first 3 phases, we need to ask ourselves, have we the resources available to extract, process, and manufacture the raw material of interest? Next is assembly. the building parts we have manufactured. Product use over the development life cycle. A factor we need to consider here is what maintenance is required over the development life. And finally, what will happen to the development at its end of life. So before we begin to examine the various stages, let's take a quick look at some of the essential skill training that engineers require. Firstly, building information modeling. It's a process that begins with the creation of an intelligent 3D building model and enables us to document, manage, coordinate, and simulate during the entire life cycle of a project: plan, design, build, operate, and maintenance. There's a video from Autodesk that gives a clear outline to how BIM can extremely be beneficial towards our built environment, new and existing developments. Some of the key points from Autodesk are: engineers, architects, contractors, and all other stakeholders can work together efficiently and effectively on a live updating model. It allows all developments to be designed, built, operated, and monitored, and it becomes much easier to keep lifecycle assessment as an active part of lifecycle over the entire lifecycle. So why is BIM essential for sustainability? Live updating of the building model, all stakeholders working off the same live model. This eliminates the possibility for works to be completed on an old drawing, improves the time and work and efficiency of the project. From this live model, we can automatically calculate the exact quantity of material that we require. Since we are working on a live updating model, any changes will be incorporated into the material procurement process. This requires the possibility for large quantities of waste in the production and construction process. Next, we have the programming of the development, which is more accurate. All stakeholders know that they need to start and finish their part of the project. Health and safety is incorporated into the live model. Method statements are built into live model for employees to read and understand on how to complete a task. This makes sure that the project can be delivered in the safest possible manner. Safety on site and preventing fatalities should be the number one concern as we continue to tackle the Anthropocene epoch. We can also carry out automatic carbon emission calculations. The BIM model can be used to compute the carbon emissions from the project during the production, construction phase, and also for the life cycle of the project. This can be used in the feasibility study and gives a good indication on whether a project is in line for the preferred green building or living accreditation. And last but not least, life cycle monitoring. Monitoring of the development must be carried out over its life cycle. This can be done using remote structural monitoring by using sensors throughout the structure to monitor the structure behavior, deflections, deteriorations, corrosion, sway, etc. This will give indications of when maintenance, repair, or demolition is required. In-person inspections could also be carried out with the results inputted into the development live model. Raw material selection process. Starting with the first phase from the life cycle assessment, common raw materials for engineering and construction: limestone, mining for cement production; iron ore, mining for steel production; timber for harvesting for timber production. Once again, we have limestone for mining for glass production and crude oil drilling for plastic production. In the material selection process, what do we need to consider when choosing a raw material? Material availability. Is the material available in this country, or do we need to import it from another country? Material extraction resources. In extracting raw materials from the earth, whether it be timber, limestone, iron ore, or oil, do we have the extraction resources available to us? Environmental impact. This is the one which is the most important factor for delivering a sustainable development. Pollutions that must be considered when selecting a material are dust, noise, watercourses, energy usage, water usage, etc. Cost of raw material. All costs should be analysed and compared for the materials considered. Various factors to that various factors that need to be considered. Is it a specialized material? Supply versus demand, location of material sourcing, care is required to ensure all taxes are included in the price estimation. An example of this in the UK, which has just left Europe. Additional taxes will be charged for materials purchased in the UK from EU consumers. 5. Logistic feasibility, where resources are available to develop the raw material to the production plant. If the material source is in the same country, look at the various options: articulated trailers, train haulage, barges, etc. And finally, labour skill set available for raw material. A new or specialized material usually requires a specialized team. Do we have this labor resource available to us? Material processing and design capabilities. So this is the next stage of the life cycle assessment. Looking from going round. A, cement production with the limestone extracted. B, steel production using the iron ore extracted. C, manufacturing of timber lengths using wood logs harvested. D, glass production using the limestone extracted. And finally, we have the production of PVC pipes using crude oil drilled from the earth. Factors to consider when choosing a material to manufacture. Manufacturing resources available. Have we the resources available to produce raw glass, steel, plastic for the part manufacturing phase? Number 2, environmental impact. Producing cement through the kiln rotation process requires very high energy. This is due to the extensive heat required to transform the raw materials to clinker. Comparing this process to timber manufacturing, it's mainly CNC machines cutting that is carried out, which does not require extremely large amounts of energy. Cost of production process. If the production resources are not available to us, it may cause heavy financial burdens to purchase the required equipment. This should be a key factor considered in the material selection process. The question that should be asked by manufacturers is, what future is there for this material in the built environment, and would there be contract for the production of raw materials for the next 10, 15, 20 years? Number 4, logistic capabilities. What resources are available to deliver the material to the site or to the production plant? Is the raw material source in the same country? What are the various options for reducing transport emissions? Articulated trailers, train haulage, barges, etc. 5. Labour skill set available for a material. If the labour resource is not available for a material, people need to be hired for the project of a contract basis, or else the material may not be suitable. Attempting to manufacture a material with a crew that has very little experience with the material may lead to great additional costs and delays. And number 6, design competency. Training and design resources available to complete a project. Have we the adequate material designers, or will we need to contract specialized designers in to clean up our design mess? As for resources available to us, is your employer intending on paying for required training and design packages required to deliver a project, e.g. cement production?